We've now pretty thoroughly developed the theory of integration of non-negative measurable functions. That's not a rich enough class for our interests. Our random variables are of course going to take both positive and negative values. So let's extend our integral to that case, even allowing for some small amount of infinite values. Let f be a measurable function on a measure space, taking values in the extended real line, and here we mean measurable with respect to the sigma field in the domain and the Borel sigma field in the range. Recall that we have this nice decomposition of any such function f in terms of its positive and negative parts. Those two functions are non-negative measurable functions, and we can reconstitute our function as the difference between them. Now we want our integral in the general setting to still be a linear function to respect addition and scalar multiplication, and so that means there's really only one way we can extend our integral to functions that take positive and negative values, and that is to define the integral of f, which is the integral of f plus minus f minus, to be the integral of f plus minus the integral of f minus. Now, let's be careful here. This could potentially be something of the form infinity minus infinity. And there is no good consistent way to rule that out, and so we just won't try to make this definition unless that doesn't happen. We're only going to define this general Lebesgue integral for functions that are integrable. Integrable means that the positive and negative parts of the function integrate to values that are finite. The set of all such measurable functions for which f plus and f minus have finite Lebesgue integral is called L1. And this definition of the integral makes sense for L1 functions. Now, let's note one quick thing here. The absolute value of our function can be reconstituted as the sum of its positive and negative parts. And because everything inside is measurable, we can just as well define this set L1 as the set of measurable functions taking extended real values for which the integral of the absolute value of the function is finite. In all of these cases, we are leveraging the definition we've already made for the integral of non-negative functions, and then just applying it to some positive functions that are related to our now general real-valued function. Now let's notice one important thing. The condition for being in L1, that either the absolute value of our function or its positive and negative parts take finite values, implies, from an argument in the last lecture, that the functions themselves, f plus and f minus, take finite values at all but a null set of points in the domain. And therefore, by restricting our attention to complements of null sets, we may as well assume that our functions are always actually real valued. That doesn't mean that they can't explode as you approach some asymptote, like in the classical Riemann integral case. It just means that the actual value at any point may as well assumed to be a real number. With this definition in hand, we can now proceed to state and quickly prove all of the basic properties of the integral for non-negative functions which hold for L1 functions. L1, this space of functions whose absolute integral is finite, is a vector space under the reals. The integral is a linear functional on that vector space, and it is positive. It's order preserving. If f is less than or equal to g, and we know we may as well say that more generally, if it's true almost surely, implies that the integral of f is less than or equal to the integral of g. Let's run through basically how to prove these things. First, for L1 being a vector space, if we take two functions, f and g, that are in L1, and we look at some linear combination of those functions, well, the absolute value of that is, by the usual triangle inequality on the real line, less than or equal to the absolute value of a times the absolute value of f plus the absolute value of b times the absolute value of g. And notice that everything on both sides here are L plus, positive measurable functions. And therefore, using the properties of the integral for non-negative functions, we can note that the integral of the absolute value of AF plus BG d mu, well, that's going to be, by the monotonicity property of the integral we already developed, less than or equal to the integral of the absolute value of everything inside, which, using the linearity properties of the integral for positive functions, is equal to absolute value of a times the integral of f plus the absolute value of b times the integral of g. And by assumption, f and g are in L1, therefore this is less than infinity and this is less than infinity, which means that therefore this whole thing is less than infinity, which is to say that AF plus BG is back in L1. That shows that L1 is a vector space. As for the linearity of the integral, if we integrate AF, well, by definition, we have to write AF in terms of its positive and negative parts. So that's defined to be the integral of the positive part of AF minus the integral of the negative part of AF. Now, what's the positive part of AF? Well, that's going to depend on the sign of A. If A is 0, everything is silly, and we don't even need to think about it. Let's just treat the case where A is positive here. So if A is positive, then the positive part of AF is A times the positive part of F, as you can quickly verify. And so we'll get this. Similarly, the negative part of AF will be the negative part of F times A. And now we use the linearity of the integral of non-negative functions to pull the A out in both cases and recombine, noting that the integral of f plus minus the integral of f minus is our new definition of the integral of f, and so we're done. In the case where A is negative, we get a switcheroo. The positive part of AF is the negative of A times the negative part of F, and similarly for F minus. I won't write out the details, but leave it to you. Now finally, we need to check the linearity of the integral here. So let's just integrate f plus g. Well, f plus g is f plus minus f minus plus g plus minus g minus. And now we need to write that in terms of its positive and negative parts. It's pretty easy to see that that's going to be f plus g plus as the positive part, and f minus plus g minus as the negative part. Now we use the linearity of the integral over non-negative functions in both cases, and we recombine. And I'm just going to write that because we're running out of space and nothing interesting is going to happen here. That will show that the integral respects addition in general. For the positivity claim, we argue similarly. Suppose f is less than or equal to g, almost surely. We'd like to compute the integral of f and the integral of g and compare them. That means we need to break up f and g in terms of their positive and negative parts. Well, f is f plus minus f minus, and our assumption is that on a set of full measure, that's less than or equal to g, which is g plus minus g minus. And so therefore, on that set of full measure, by adding and subtracting accordingly here, we see that f plus g minus is less than or equal to g plus f minus. Now using the monotonicity property for the integral on non-negative functions, we get that the integral of f plus g minus is less than or equal to the integral of g plus f minus. By linearity of the integral, which actually now holds in general, as we just saw, this is the integral of f plus the integral of g minus. And on the right-hand side, that's the integral of g plus the integral of f minus. And now, by again adding and subtracting appropriately, that tells us that the integral of f plus minus the integral of f minus is less than or equal to the integral of g plus minus the integral of g minus. But this is the definition of the integral of f, and this is the definition of the integral of g, and that concludes the proof. And by the way, let's include that same bonus statement that we did last time. The absolute value of the integral is less than or equal to the integral of the absolute value. We proved that for the integral of simple functions. Now we'll see that it holds in general for the integral of L1 functions, just by definition, because this on the left-hand side is the integral of f plus minus the integral of f minus, by the triangle inequality in the real line that's less than or equal to the absolute value of the integral of f plus plus the absolute value of the integral of f minus, but those are integrals of non-negative functions which take non-negative values. Therefore, this is equal to the integral of f plus plus the integral of f minus. By the linearity that we just proved, that's equal to the integral of f plus plus f minus. But f plus plus f minus is the absolute value of f, and that gives us our desired inequality. So that's the Lebesgue integral, and now we know how to compute expectations of random variables. If x is a random variable in a probability space, if it happens to be L1, then its expectation is defined to be the integral of x with respect to the probability measure. Wonderful. But how do we actually compute that in any case where the random variable is not a simple random variable? Well, that's an excellent question, and we will address that. But before we do, let's talk a little bit more about the robustness of this integral and how it interacts with sets of measure 0. We're now going to introduce an ostensibly different set of integrable functions, L1, instead of scripty L1. To motivate this, let's remember our construction of measures in the first place using the pseudometric of a premeasure. Of course, now that we know that the premeasure extends in the cases we're interested in, that pseudometric is actually defined in terms of the measure. That is, if I have any two subsets, A and B, of our sample space, they don't need to be in the sigma field for this definition to make sense, the pseudometric distance between them, induced by the measure, is the outer measure of the symmetric difference of those two sets. Now, if those two sets happen to be in the sigma field, then, as we proved, the outer measure coincides with the measure, and so that's just the measure of the symmetric difference of the two sets. As you've shown on your homework recently, we can rewrite this in an effective way, following the trick of writing measures of events as integrals of their indicator functions. This can be written as the integral of the indicator function of the symmetric difference, but a nicer way to write it is as the integral of the difference between the indicator functions, which is the same as the indicator of the symmetric difference, provided that you take the absolute value. Motivated from that, let's remember that we can think of our sigma field as being contained in the set of non-negative measurable functions. We think of an event as being in correspondence with its indicator function, which is a non-negative measurable function. If we were in a finite measure space, then all of these functions would be L1, because the integral of an indicator is the measure of the set that it indicates, and those measures would all be finite. In general, these things are not in L1 because there are sets with infinite measure, but in a probability space, they will be in L1. Now, this presents a nice way to extend the pseudometric defined on sets, at least those sets that have finite measure, all the way to L1. We'll define the L1 norm, written like this, of functions in L1 to be the integral of their absolute value. That is called a norm, which we'll explore on the next slide, but let me just note that the pseudometric of two measurable sets, which is the integral of the absolute value of the difference of their indicator functions, is therefore just the L1 norm of the difference between those two functions. The norm of a difference sets up a metric, and that's what our pseudometric really is. It's the metric induced by the L1 norm. But why am I calling it a pseudometric instead of a metric? In fact, it's not a metric. In general, it's only a pseudometric. And in fact, the L1 norm, the way that we've constructed it here, is not a norm. It is only a seminorm. Let's remind ourselves of the definition. If I have an arbitrary vector space V, a norm on that vector space is a function from the vector space into the non-negative real numbers that satisfies these properties. It's sublinear in the sense that It respects scalars. The norm of alpha times f is the absolute value of alpha times the norm of f for any f in the vector space and any constant alpha. And the norm of a sum is less than or equal to the sum of the norms. A third and very important property that makes a norm is that it separates points, which means that the norm of a vector is 0 if and only if that vector is actually the 0 vector. Now the if part of this actually follows from the first property, taking alpha equal to 0. But the only if property is special, and if it fails, then we don't call this function a norm, it's called a seminorm. We should probably call it a pseudonorm to be consistent with our notation for metrics, but the notation is what it is. In general, if we have a norm, then we can define a metric from it by taking the norm of the difference. And it is easy to check from this sublinear property that all the properties of a norm hold, in particular the triangle inequality, which is equivalent in this context to that sublinear property. But a genuine metric has to separate points, and that will only happen if the norm is a genuine norm. If there are vectors that are not the 0 vector but have norm 0, then there will be points in our space that are 0 distance apart but are distinct. But that's okay, as we've seen before. In general, if we have a seminorm, like this, where everything holds except for the possibility of having some non-zero vectors have norm 0, then this defines a pseudometric. So here's the deal. The L1 norm is actually a seminorm on L1, but it's not a norm. To see that it's a seminorm, we just check each of the properties, and most of them are practically immediate. Just remember that the L1 norm of a function is defined to be the integral of its absolute value against the measure. So the fact that it takes non-negative values and respects scalars in this way are basic properties of the integral that we proved several lectures ago. To check the sublinear property, we just do a quick calculation. The L1 norm of the sum of two functions, which is the integral of the absolute value of the sum. The absolute value of the sum, pointwise, is less than or equal to the sum of the absolute values of the two functions, and so by the monotonicity property of the integral of non-negative functions, this is less than or equal to the integral of the absolute value of f plus the absolute value of g. And now, since f and g are both L1, we know that that is equal to the integral of f plus the integral of g, absolute value, which is the L1 norm of f plus the L1 norm of g as desired. So all of the properties of a seminorm are verified, but it's not a genuine norm, typically, because we see that the L1 norm being 0, which means that the integral of the absolute value of this function is 0, well, the absolute value is a non-negative function, and as we proved last time, this happens if and only if that non-negative function is equal to 0, almost surely with respect to the measure. And of course, since the absolute value of a number is 0 if and only if the number is 0, that means that the norm of a function is 0 if and only if it is 0 almost surely. But that doesn't mean that it's 0. It just means that it's 0 off of an arbitrary null set. And that's why this L1 space, equipped with this function, is not a norm space, it is a seminorm space. There is, however, an abstract nonsense fix for this, which is to just divide out by the non-norminess. That is to say, we define an equivalence relation on script L1 by saying that two functions are equivalent if and only if they agree on a set of full measure. They are equal almost surely with respect to the measure in question. It's easy to check that this induces an equivalence relation on script L1. And so we define non-script L1, which is the notation we'll use from now on, to be the quotient of script L1 by that equivalence relation. That is to say, the elements of L1 are equivalence classes of functions, where for a given element of L1, two functions in that element, in that equivalence class, agree almost everywhere. In measure theory, we have a nice term for this, Given such an equivalence class, any function that you choose from it is called a version of that equivalence class. It will frequently be useful to change the version of our function and say, look, by modifying it at a set of measures 0, I haven't changed any of the basic properties with respect to the integral that I care about, and so I can change versions at will in most situations. Now, script L1 was more than just a set, it was a vector space, and it's again not a hard calculation to show that if you define the sum of two of these equivalence classes of functions to be the equivalence class of their sum, and if we define scalar multiplication similarly, these are well defined. And that turns L1 into a vector space. Now, how about the integral? Well, if I have two functions that agree almost everywhere, then their integrals agree. That was part of proposition 10.11 that we proved last time. And therefore, we can also define the integral of an equivalence class of functions in L1 to be the integral of any version of the function in there. And that makes perfect sense. And it is now boring and routine to verify that this descended integral on L1 satisfies all of the properties that we have now proved for the integral. It is a linear functional, it is positive, and even better, it makes the L1 norm into a genuine norm. That is to say, if the L1 norm of an equivalence class of functions is equal to 0, that means that, well, any one of those functions must be 0 almost surely, which is to say that in L1, that equivalence class of functions is the 0 element of that vector space. And so now we have a genuine norm. Alternatively, we could say that we can define this metric, which is an extension of the pseudo-metric on events, to be the L1 norm of the difference, and that becomes a genuine metric on L1, because we have divided out the kernel that makes it not separate points. Now that might sound like a bunch of abstract mumbo-jumbo, and in a certain sense it is for our purposes. So, going forward, we're going to forget about script L1, and we're going to treat L1 as if it was composed of actual functions. Just always keeping in mind that we have to sometimes choose and change versions of the function in order for statements to make sense. Now there are some persnickety times where that can be challenging, especially in the very sophisticated material at the end of this course, and when that happens, we'll make sure to make it clear. But most of the time, it's not going to present any problem at all. Let me note that we will in general use a larger family of norm spaces of integrable type functions called LP spaces for p bigger than or equal to 1. LP of a measure space is defined to be, as usual, equivalence classes under this equivalence relation of functions that are measurable and for which the Lebesgue integral of the absolute value to the pth power is less than infinity. And for such functions, we can then define the LP norm to be this quantity here. You take the integral of the pth power of the absolute value, and then you take the pth root of that non-negative number. And it is a theorem that defines a norm for any p bigger than or equal to 1. And moreover, it is actually a complete norm, which means Cauchy complete. If I have a Cauchy sequence in this norm space, then it has a limit in the norm space. We will come back to that later on in this full year course when we start to talk about different modes of convergence for random variables. We'll also talk about a generalization of this for p equal to infinity as well. We're not going to make any attempt to prove this right now. I'll just note that when p is bigger than 1, perhaps the hardest part is showing that this putative norm actually has the subadditive property that it needs to have. Proving that requires something called Minkowski's inequality, which is interesting in its own right. For now, we will focus our attention on L1. Now, to round out this lecture, We've spent the last several lectures developing some nice robustness properties for the integral, but until today, we only knew how to integrate non-negative functions. We had two robustness theorems, the monotone convergence theorem and Fatou's lemma, that allow us to say meaningful things about integrals of limits of sequences of measurable functions. Those were stated only for non-negative functions. In both cases, they can be partially generalized to now L1 functions that can take positive and negative values. But even in those forms, they aren't usually powerful enough to help us in many applications. So we're now going to state and prove a more powerful robustness result that we will use very frequently throughout this course. And it is called the Dominated Convergence Theorem. In this general form that I've written here, it says the following. Suppose I have a sequence of functions fn that are measurable and in L1, and I have another sequence of functions gn that are non-negative and in L1 that dominate them. That is, the absolute value of fn is less than or equal to gn. Now, if those gn's are known to converge to a function, almost surely, and moreover, if the integral of the gn's converge to the integral of g, and if we know that the sequence fn that's dominated by gn converges to some function f almost surely, then we can conclude that that limit function f is actually in L1, and moreover, the integral of fn converges to the integral of f. That's a mouthful. Let me point out right now that a typical application of this, in fact, a typical way that this is stated in a weaker form, is to take gn constantly equal to g for all n. In other words, that would say that if I have a sequence of functions fn in L1 that are all dominated by a fixed L1 non-negative function g, and if fn converges almost surely to some function f, then that implies that that limit function is in L1, and the integral of fn converges to the integral of f. That's the typical statement of the dominated convergence theorem, but we will definitely find times when this more general statement is useful, and the proof is no harder. Let me also note that, especially in probability theory, another further special case is if the measure that you're working with is a finite measure, like a probability measure. In that case, constant functions, m, less than infinity, are in L1, because the integral of m d mu is equal to m times the measure of the space, which is finite. And so if we take the dominating function in this theorem to be a constant function, that's called the bounded convergence theorem, which says that if I have a sequence fn in L1 that are uniformly bounded by m, and so actually there are in L1 automatically in that case, and if fn converges almost surely to f, then f is in L1. In fact, f is less than or equal to m almost surely, and the integral of fn converges to the integral of f. Again, this only holds true in the case where the measure space is a finite measure space. Let's go ahead and prove this general dominated convergence theorem. So again, our assumptions are that we have two sequences, fn and gn. Both of them converge to some functions f and g, where we know that g and gn are in L1, that the gn's dominate the absolute values of the fn's, and the integral of gn is known to converge to the integral of g. We must conclude from there that the limit function of the fn's is actually in L1, and that the integral of the fn's converges to the integral of f. So to prove this, we're going to use the previous robustness result that we proved, Fatou's lemma. To begin, let's take the absolute value of the limit function f, which we, for now, don't know is even in L1. Now, f is the limit, almost surely, of the fn's, and therefore its absolute value is the limit of the absolute values of the fn's. That's by our assumption 2. But the fn's are dominated by the gn's. That's by our assumption 3. And the limit of the gn's is g. That's assumption 2. All of this is taking place on a set of full measure, which we can fix from the outset. Therefore, it follows from the monotonicity property of the integral that the integral of the absolute value of f is less than or equal to the integral of the absolute value of g, or just of g since g is positive. And that is assumed to be finite because g is in L1. So that's by assumption 1. So we now conclude that the integral of the absolute value of f is finite, meaning that f is indeed in L1, giving us the first desired conclusion. Now, to prove that the integral of the fn's converges to the integral of f, we're going to be sneaky and consider the following. Let's integrate g plus f. We're also going to integrate g minus f, and we'll do them simultaneously, carefully. The integral of g plus or minus f, well, g and f are the limits of gn and fn, almost surely, and so integrating them, that's true. And the limit is the same as the lim inf, since the limit exists. So this is the same as the integral of the lim inf of that sum, or difference, of the two functions. And now we'll apply Fatou's lemma, which applies here because fn is dominated by g, which means that gn plus or minus fn is always non-negative, which is the case where we've proven Fatou's lemma to apply. Therefore, we can, by Fatou, pull out the lim inf from the integral at the cost of possibly increasing the size. Now we use the linearity of the integral, and we get the lim inf of the integral of gn, which we actually know is a limit by assumption 4. This is just the integral of g. Plus the lim inf of plus or minus the integral of fn. So putting that together, what we've shown is that this, which by linearity of the integral is the integral of g plus or minus the integral of f, is less than or equal to the integral of g plus either the lim inf of the integral of fn or minus the lim sup of the integral of fn. And that's just because the lim inf of minus an is equal to minus the lim sup of an. Okay, now let's cancel the integral of g on both sides there, and what we get is that the integral of f is, well, less than or equal to the lim inf of the integral of fn in the case where we had a positive sign, or that minus the integral of f is less than or equal to minus the lim sup of the integral of fn. So if we put those together appropriately and reverse the inequality in the negative case, what we've actually shown is that the integral of f is less than or equal to the lim inf of the integrals of fn and greater than or equal to the lim sup of the integrals of fn. But hey, the lim inf is always less than or equal to the lim sup. And that means that this chain of inequalities is actually a chain of equalities. And that shows us that the limit exists, since the lim sup equals the lim inf, and that that limit is equal to the integral of f, which is exactly what we wanted to show.